morning. I'm glad to be here with you today. I'm Dr. Mona Faraji Niri. I'm a senior research fellow here in WMG, a member of the Energy Systems Group, and I'm specialized in modeling, simulation, machine learning for lithium-ion batteries. And today I'm going to talk about my line of research, which is machine learning for the future lithium-ion battery manufacturing. So basically today I'm going to talk about how machine learning is going to support the future lithium-ion battery manufacturing need. So the capacity of lithium-ion batteries entering the global market is expected to grow from about 185 gigawatt hours at 2020 to about 2,700 gigawatt hours by 2030. And that means about 140 billion lithium-ion cells of the regular type. Just to give you an idea of how big that number is, if you consider a regular lithium-ion cell, which usually comes in the cylindrical format, they are usually 7 centimeters in length and about 20 watt-hours in energy capacity, and you stack those 140 billion regular cells, one on the top of the other, for 140 billion. So basically you get about 6 million miles of lithium-ion cells, and that is equal to the distance between the Earth and the Moon. So basically with that distance you can travel between Earth and the Moon for about 8 times, and that's just in one single year. So we need this huge number of the batteries to power our electric cars, electric motorcycles, e-scooters, and even our portable devices such as mobile phones or laptops, etc. Not only we need a lot of batteries, we need very high quality batteries, and by that we mean batteries that can live longer. So for example, if you are using an e-scooter, you don't want to change it in a year or two. We need batteries that can keep more charge. If you are playing with your gaming console, you don't want to get it charged more frequently. And we want them to be fast chargeable. So if you are driving your electric vehicle and you run out of charge somewhere in the middle of the road, you want to get it to the charger point and get it charged quite fast. So we need a lot of battery, and we need high quality batteries. But how we make them, how we manufacture this huge number of very high quality cells. So battery manufacturing process is actually a very long and a very consecutive process. So it is made up of different steps at different stages. And in a fantastic analogy, it's been compared with how we bake a cake. So how we make a battery is very similar to how we make a cake. So for baking a cake, you start with some ingredients like flour, butter, eggs. You mix them together, you pour them on the oven trays, bake them inside the ovens, you cut them, you shape them, and then you have your cake. That's exactly what we do for the batteries. Obviously, we don't have the flour and the egg. We have our dry and the liquid mixes. We mix them together. We don't have oven tray. What we call them is current collectors or the foils. We pour that slurry on the current collectors. We put them inside literally ovens. We let them dry, and then we cut them. We stack them one on the top of the other. We assemble them, and finally they're ready to go. We can test them, and they're ready to be used in any applications. So when you have your cake, you can taste it and understand if the quality is enough, if that's what you wanted to get. But with the batteries, we need to have some different equipment to test each and every single of the cells that we make. And probably you can imagine how much of energy, money, workforce, and the material is involved in that process. And what we are making is not that perfect. We need to test different combinations. So according to the literature and based on the experience, this manufacturing process has a lot of control variables and a lot of parameters to be set. So, such as the temperature of the ovens, the mixing speed, the drying time, the drying temperature itself. And this different combination of the parameters gives us different quality of cells in terms of its capacity, its lifetime, its charging time, and etc. According to the literature, we have about 600 of these variables, and you can imagine how big that number of different combinations can be. What if we could predict the performance of our cells before making them within the labs without getting our hands dirty? So can we do that? Can we predict the performance before making them? If we could, that means saving a lot of money, a lot of workforce, a lot of energy, and reducing the waste of the material when the result of the manufacturing is not the perfect thing. So the answer to the question is yes, we can. And this is what we're doing here with the help of AI and machine learning. So AI and machine learning are a set of algorithms that help us to train our computers to think just like a human. So AI and machine learning algorithms are those kind of algorithms that help the computers to extract the relationships between the control parameters and the control variables and the quality indices of any output. How we do this is like basically how we train a baby. So when you're a baby, you basically have no idea about anything. So if you show this image to a baby and ask which one's a cat or a croissant, he or she probably won't be able to answer. So how to teach her or him is you show some examples. This is a cat, this is a croissant, and as the baby grows, they can generalize. So basically, this is what we do with our computers. Obviously, instead of a baby, we have a computer. Instead of these cats and croissants, we have our batteries with different quality indices. And instead of that person showing the images, we have our data scientists. So our data scientists are introducing some kind of examples coming from the experiments, the real experiments in the lab, to the computers, training those algorithms, and eventually the computer can help us to distinguish between the different cells with different quality indices. So we can separate good and bad batteries without necessarily making them, by generalizing those limited number of the experiments to more and more scenarios. So this means that instead of making those cells within the labs, we can predict their performance beforehand. So we can avoid ending up with cells that are necessarily good in quality for us. And this means saving a huge amount of money because this testing equipment usually are very expensive. The very regular one of those is coming at the size of a household fridge, and they're quite expensive. So we can eliminate the need to testing those cells because we already know that it's not going to work. And we have saved a lot of material from going to the waste because we already know that the output is not going to be what we want. So having these facilities and this kind of algorithms would help us to move forward a better set of batteries that can live longer, batteries that can keep charge for more, and batteries that can be manufactured more sustainable because we have limited the waste of the material and the amount of the workforce and money that is required. And this means building jobs and also introducing new kind of careers to the battery industry. Thanks for listening. I hope you've enjoyed it.